Welcome to the Deep Dive. We're the place where we really get into the weeds on complex topics, digging through sources, notes, all that stuff, to find what really matters.
That's the plan.
And our mission today, well, it's a journey back to the 1980s. We're going to explore a really audacious vision in computing, the Inmos Transputer.
Ah, yes, the Transputer. A fascinating piece of kit.
Exactly. We're planning to uncover its history, which is quite a story in itself. We'll delve into its unique design, what made it tick.
And analyze its strengths and weaknesses, definitely. What worked, what didn't, especially for its time.
Right. And maybe most importantly, reveal its, kind of surprising impact on the CPUs we all use today. It wasn't designed to be a solo act, was it?
Not at all. That's the key thing. From day one, it was conceived as part of a team, a cluster of processors working together. Really unique for the time.
So to get there, we need to set the scene. The 1980s. What was the big problem computer architects were facing?
Oh, it was a fundamental wall. People started calling it the von Neumann bottleneck. It sounds technical, but the idea is pretty simple.
Oh, well.
Imagine you have this incredibly fast processor, like lightning fast, doing calculations in nanoseconds, billionths of a second.
Okay, sounds good so far.
But it's constantly waiting for data to arrive from memory, waiting to send its results back out. And this data has to travel along physical wires.
Right, the plumbing of the computer.
Exactly. And even moving at, say, half the speed of light, which sounds fast, getting data across those wires could take 10 times longer than the actual calculation.
10 times. Wow, so the processor's just idling most of the time?
Pretty much. It's like having a Formula One engine stuck in city traffic. All that power, but bottlenecked by the connections.
And it wasn't just speed, was it? There was another big issue. Heat.
Oh, absolutely critical. You're cramming millions, eventually billions, of these tiny transistors onto chips. They switch incredibly fast.
Which is good for performance.
Yes, but every switch consumes energy, and that energy turns into heat. A lot of heat, especially when packed so densely.
And silicon chips, they don't like getting too hot, right?
They really don't. Silicon has a pretty narrow happy zone temperature-wise. Push it too far and performance degrades, or it just stops working.
Yeah.
Fails completely.
So the supercomputers back then needed serious cooling.
You bet. People joked they were basically very small, very efficient refrigerators that happened to do some calculations on the side. It was a constant battle against heat.
So just making things smaller wasn't the whole answer.
No, because that often just concentrated the heat problem. Traditional single processor machines, the standard von Neumann architecture, even the big ones like the DEC of VDEX 11750, they were hitting these fundamental limits, performance ceilings.
Okay, so the old way was running out of steam. What was the alternative?
Well, this impending crisis, this bottleneck, led directly to a pretty radical idea. Parallel processing.
Parallel, meaning doing lots of things at once.
Precisely. Instead of one super fast brain tackling a huge problem step by step, you break the problem down, chop it into lots of smaller, independent pieces.
Okay.
Then you give each piece to a separate processor. And here's the key. They all work on their piece at the same time, simultaneously.
So the total time to solve the big problem gets much shorter.
Potentially, dramatically shorter, especially for problems that naturally break down into parallel tasks like simulations or image processing, that kind of thing.
And this wasn't just theory. People were actually trying to build these things.
Oh, yes. Researchers were deep into it. Columbia University, for instance, had a project called non-von Neumann, started around January 85.
What was their goal?
Their ambition was huge. They wanted to build machines with literally millions of small, fairly simple 8-bit processors.
Millions? Wow.
Yeah. Think of each one like a tiny little personal computer, its own processor, its own little chunk of local memory, each one handling its own piece of the data independently.
Sounds incredibly powerful. But how do you get millions of processors to work together?
Yeah.
That sounds like chaos.
That was the absolute killer problem, the Everest of parallel computing, as you say. Communication and coordination.
Right. Getting them all to talk to each other efficiently, sharing results, not tripping over each other.
Exactly. Imagine trying to orchestrate a million tiny computers. How do you connect them? How do you pass messages? How do you synchronize their work? Without a really smart integrated design, it just becomes an unmanageable spaghetti junction of wires and complexity.
Okay, so that sets the stage perfectly. Which brings us back to our main topic.
The Transputer.
The Inmos Transputer. Because this wasn't just a university research project, this was a commercial effort, right? from a company in Bristol in the UK.
Yes, Inmos. They were trying to take this parallel vision and make it a real product you could buy, a pioneering effort.
So that's our mission for this deep dive. We're going to unpack the whole story, its history, its unique design.
The good bits and the bad bits, the advantages and disadvantages it had at the time.
And crucially, how it influenced what came later. How it shaped the CPUs we rely on today. Because as you said, its whole identity was being part of a team, designed to be clustered.
Absolutely. It wasn't meant to be a loner. Its power came from cooperation.
Okay, let's dig a bit deeper into that von Neumann bottleneck first. You said the processor was fast, but the wires were slow.
Relatively speaking, yes. By the 80s, transistors were ridiculously fast, switching in billionths of a second, performing complex logic almost instantaneously.
Not the data.
The data had to physically move across the chip, between chips, to memory and back. Even short distances take time, especially when you compare it to the speed of the transistors themselves.
And that time adds up.
Massively. That 10-to-1 ratio we mentioned, calculation time versus data travel time, that was a real killer. It didn't matter how much faster you made the processor if it spent most of its time just waiting for data, a fundamental choke point.
And the heat problem wasn't just like an inconvenience. It was a hard physical limit.
It really was. Those fast switching speeds generate heat, lots of it. Cram more transistors into a smaller space, you get more heat in a smaller area.
And silicon just can't handle it beyond a certain point.
Right. Its electrical properties go haywire. You get errors, instability, or just complete chip failure. So you needed those complex, often expensive cooling systems. Elaborate refrigeration, sometimes liquid cooling.
Which meant simply shrinking things further wasn't a magic bullet.
Not on its own, no. It could actually make the thermal problem worse. You needed a different approach entirely.
And that different approach was the non-von Neumann parallel idea. You mentioned processors were getting cheaper.
Yes, that was a key economic driver. The chips themselves, the silicon with the transistors, were becoming relatively inexpensive compared to the rest of the computer system. Memory, storage, peripherals.
So instead of one hugely expensive, complex processor.
It started making economic sense to use lots of simpler, cheaper processors working together. Get more bang for your buck, computationally speaking.
Like that non-von project at Columbia. Lots of small processors.
Exactly. Their design aimed for vast numbers. Each processor was, roughly comparable to a basic PC of the time. But the key was each one got its own instructions, had its own little local memory store.
Processing its own data independently?
Correct. Completely independent operations happening simultaneously across the machine.
How did they organize them? You mentioned millions. How do you connect them?
They explored different structures. A key one was the binary tree. Imagine a top processor connected to two below it, each of those connected to two more, and so on. It creates this branching structure.
Like an organizational chart.
Sort of, yeah. Their initial setup had, I think, 64 processors on separate chips, but the plan was to integrate. Put maybe 8 processors already in a tree structure onto a single chip.
And scale that up.
Massively. The dream was literally 1 million processors in one machine eventually. The potential performance was just mind-boggling for the time.
But the software, that was the catch, right?
Yeah.
Existing languages weren't built for this.
Not at all. Fortran, C, Pascal, they were all sequential, designed for one processor doing one thing after another. The parallel approach was, as they put it, very foreign.
So how did non-von handle that?
They developed a parallel version of Lisp, which is a language well-suited to certain types of symbolic processing. And for specific calculations, especially ones easily broken down, they saw huge speed-ups.
Like how much faster?
Sometimes 100 times faster than traditional methods, which really showed the potential if you could crack the software problem.
You mentioned an example earlier about giving raises.
Yeah, the salary raise example. It illustrates the concept beautifully. Imagine your company database. Each employee record is stored on a separate little processor in this non-von machine.
Okay.
Now, you want to give everyone in the sales department a 10% raise. You broadcast instructions to all processors simultaneously.
Like shouting orders to an army.
Pretty much. First instruction, check your department field. If it's not sales, go to sleep for a bit. Poof, all non-sales processors switch off. Next instruction, if you're still awake, take your salary field and multiply it by 1.1, where all the sales processors update their local salary data.
Simultaneously.
Exactly. Then a final instruction, everybody wake up. The beauty is the whole operation takes a fixed amount of time, no matter if you have 100 employees or 100,000, because it all happens in parallel, fixed time operations.
That's a powerful idea. Okay, so against that background of bottlenecks, heat, and the promise of parallelism.
Comes Inmos. Based in Bristol, UK, they had their own take on this parallel future, a commercial one.
With their chip, the transputer.
The transputer, a single chip but packing a punch, a 32-bit processor, its own memory right there on the silicon.
And built-in links to talk to other transputers.
That was the killer feature, designed for networking from the start.
And Inmos wasn't messing around. They wanted to change the game, challenge Intel, the big boys.
Absolutely audacious ambition. They weren't just designing chips, they were building their own factories, their own fabs, even making memory chips. Total vertical integration, almost unheard of for a startup.
It was a massive gamble. So the big question hanging over it all, decades ahead of its time. Or just a brilliant idea that couldn't quite make it.
That's the core of the story, isn't it? Let's find out.
So Inmos, how did this incredibly ambitious company even get started? Sounds like a bit of a story.
It really is. Quite a charming origin, actually. It supposedly started in a bar in Toronto back in 1977.
A bar, okay.
Yeah. Richard Petritz, who's a big name, he'd been at Texas Instruments, founded Mostek, a major semiconductor player. He apparently just asked Ian Barron, a British computer entrepreneur, how would you like to set up a semiconductor company? Just like that.
Wow. Bold opening line.
Petritz was convinced of two things. First, VLSI, very large-scale integration, packing millions of transistors on a chip, was about to completely revolutionize semiconductors.
Right, the density was exploding.
And second, the shift from older bipolar technology to the newer, more efficient MOS technology, metal oxide semiconductor, would open the door for new companies to challenge the old guard.
And Barron, what was his angle?
Barron had the vision for a new kind of microprocessor, but crucially, he was British and didn't want to move to the US. He wanted UK funding.
Which is where the government stepped in.
Exactly. The UK's National Enterprise Board, the NEB, it was a state-sponsored investment body. Barron had done some consulting for them before.
So he had an in.
He did, and he managed to secure an absolutely staggering $50 million in 1977.
50 million pounds. In 1977 money.
Yeah, estimates put that at around $500 million in today's money. An incredible sum for an unproven startup.
That's serious commitment from the government.
It was huge. Apparently, Prime Minister Jim Callaghan himself approved it, even though there was opposition within his own Labour government about backing such a risky venture with state funds.
So it was a UK-funded but transatlantic operation.
Very much so. Design and manufacturing were split. They had facilities in Colorado Springs in the U.S., and then the UK side had the design center in Bristol and a brand new fab in Newport, Wales.
And that Newport fab was designed by someone famous.
Richard Rogers, the architect behind the Pompidou Center in Paris. Quite a statement piece for a chip factory.
But it wasn't easy starting up, right? Lawsuits, competition.
Oh, definitely not smooth sailing. Mostek, Petritz's old company, sued them over poaching engineers, and the established U.S. memory makers were already feeling the heat from Japanese competition and didn't exactly welcome another player, especially one with government backing. Inmos walked right into a firefight.
What did they make first? Not the transputer straight away.
No, their initial focus was memory, specifically 64 kilobit dynamic RAM, DRAM. Very competitive market.
That'll work out.
They hit some snags in development, so they cleverly pivoted to 16 kilobit static RAM, SRAM, the IMS 1400.
Static RAM, different type of memory.
Right. And here, they got a bit lucky, maybe strategically brilliant. Intel had announced a competing 16K SRAM chip a year earlier, but never actually shipped it.
Really? Intel dropped the ball.
Seems so. And the Japanese firms who were dominating DRAM hadn't quite jumped into this specific SRAM niche yet. So for a brief period, Inmos had a near monopoly.
Wow. What did that mean for prices?
They were selling these IMS 1400 chips for over $100 a piece, which was huge money back then. They also pushed hard on advanced manufacturing tech things like wafer steppers for precision, dry etching for cleaner processing, and redundancy, building in spare circuits to improve the number of working chips they got from each wafer.
So they were innovating on the manufacturing side too, getting good yields.
Absolutely. It showed they could execute, not just design. They weren't just dreamers.
Okay, so Inmos proved they could make and sell chips, memory chips at least. But Barron, the co-founder, his real vision was this new microprocessor.
Exactly. Memory was maybe a way to fund the bigger dream. Barron had this core belief. Just like computers were built from millions of transistors, the next generation of computers would be built from many processors working in parallel.
And that's where the transputer concept came from.
Precisely. The name itself tells the story. Transistor plus computer. It was meant to be the fundamental building block for these new parallel machines.
A programmable transistor, almost.
That's a nice way to put it. And a key requirement right from the start was hardware support for fast communication between these blocks, the links.
So inside Inmos, how did they decide what this transputer would actually look like? Was there agreement?
Not initially, no. There was a significant internal debate. The design team leaders were David May and Robert Milne.
And they had different ideas.
Very different. Milne was pushing for a design tailored specifically for the Ada programming language. Ada was seen by some, particularly in defense and aerospace, as the future, very structured, very reliable.
Okay, an Ada machine. What was May's view?
David May was heavily influenced by Professor Tony Hoare, a giant in computer science, and his ideas on communicating sequential processes, or CSP. May argued for a much simpler approach.
Simpler how?
A RISC-like design. Reduce instruction set computer. Fewer, simpler instructions executed very quickly. May believed the underlying MOS chip technology was so fast that simplicity was the key to unlocking performance. Get rid of unnecessary complexity.
So Ada-specific versus simple and fast. Who won?
Barron eventually had to step in. He apparently got tired of the debate and made the call. Go with May's simpler RISC-like approach. A really pivotal decision.
And they needed new tools to even design this thing. Fat Freddy.
Yeah, that was the code name for their internal electronic design automation, ED, tools. The existing commercial tools just weren't up to the job for something as novel as the transputer. So, a small team, just 5 people, built their own design system from scratch. Incredible effort.
So when did the world first hear about the transputer?
It was announced in 1983. And the first working silicon chips actually shipped in 1984.
1984. That's pretty early in the microprocessor game. Before ARM.
It actually predates the first ARM core, yes.
Which is interesting context. Byte magazine, which was hugely influential back then, even put it up against chips like the Intel 80286.
And that was totally different architecturally.
Completely different. But Byte saw it as part of that next wave of powerful 1632-bit processors, even if its destiny lay in parallel computing. All right, let's get into that architecture.
Yeah.
What was the core philosophy behind the transputer? You said it was designed for parallel from the start.
Absolutely. It was fundamentally the first general-purpose microprocessor conceived for parallel computing, not adapted for it, designed for it. The idea was a whole family of chips, different power levels at different costs, all designed to be wired together easily.
Like Lego bricks for building parallel computers.
That's the perfect analogy. And each brick was remarkably self-sufficient. It had a very microcontroller-like feel.
Microcontroller. Like the simple chips in embedded systems.
In the sense that it needed very little external circuitry to function. It had RAM right there on the chip, a built-in memory controller for accessing external RAM if needed, bus support, even some real-time operating system functions baked into the hardware.
So you didn't need dozens of support chips around it like other CPUs.
Much less so, yeah. It made building systems simpler and more compact. You could even boot it without a ROM chip.
How did that work?
It could receive its initial startup code over one of its serial communication links. You could literally network boot a bare transputer chip. Incredibly flexible.
But there was a big omission, something other high-end chips had.
Yes, the Memory Management Unit, or MMU. And related to that, no hardware support for virtual memory.
Why is that significant?
MMUs and virtual memory are crucial for running complex, modern operating systems like Unix. They handle memory protection, allow programs to use more memory than physically available.
Well, no MMU meant.
It meant running mainstream Unix on a transputer was very difficult, practically impossible without significant workarounds. A major departure from chips like the Motorola 68K or Intel's by 86 line.
Instead of interrupts, it had an event line.
Yeah, it had something called an event line. It functioned a bit like an interrupt signaling external events. But the clever part was how it was handled, essentially treated like just another high-priority communication channel within the transputer's process scheduling system. Very neat integration.
Okay, let's talk registers. RISC chips were famous for having lots of general-purpose registers. What about the transputer?
The opposite. Extremely minimalist. Just 6 main CPU registers.
6. That's it. What were they?
You had a workspace pointer, basically pointing to the current process's local variables in memory. An instruction pointer, obviously keeping track of the next instruction. An operand register, used for building up instruction data.
And the other three?
A tiny 3-deep evaluation stack, registers A, B, and C.
A stack, right in the CPU core.
Yeah. Most arithmetic and logical operations use these A, B, and C registers as their source and destination. When you loaded a value, it went into A pushed to B pushed to C. When you stored A, B popped back to A, C popped back to B.
That's very different from the, say, 32 general-purpose registers you'd find on a MIPS or ARM chip of the era.
Radically different. RISC philosophy was load data into lots of registers, operate on registers, store results back. The transputer used this tiny stack for immediate operations, relying more on memory via the workspace pointer.
Why? Why such a small register set? It seems counterintuitive for performance.
But there was a very specific, very clever reason. It was all about context switching.
Switching between different programs or tasks.
Exactly. In a parallel system, a processor might be juggling dozens, even hundreds, of different processes or threads concurrently. When you switch from one process to another, you have to save the current state registers and load the state of the next one.
And if you have lots of registers.
That takes time. Saving and restoring 32 registers takes longer than saving and restoring maybe just the workspace pointer and instruction pointer. The transputer's tiny register set meant context switching was incredibly fast. Almost instantaneous.
So it sacrificed general-purpose register space for ultra-fast task switching.
Precisely. It was a trade-off optimized for massively concurrent environments, which was exactly what the transputer was designed for. Hardware support for lightweight processes.
Now, the instructions themselves. RISC was about simple, fixed-length instructions. What did the transputer do?
Again, something different. The instruction set was designed for one main goal: compactness. To allow programs compiled from high-level languages, especially Occam, to be very, very dense.
Dense meaning taking up little memory.
Exactly. It had a relatively small number of core instructions, but the clever bit was the encoding. Most instructions were just a single byte long, 8 bits.
A whole instruction in 1 byte. How?
Each byte was split. The upper 4 bits defined the function code what the instruction did. The lower 4 bits often carried a small data value or operand.
What could you do with 1 byte?
Quite a lot of common stuff. Load a small constant value directly, 0 to 15. Load or store from the first 16 locations in the current process's local memory, the workspace. Basic jumps and calls, add a constant, all single byte operations.
But what if you needed a bigger constant? Or to access memory further away?
That's where the prefixing came in. There were special prefix instructions, fix and nfix, negative prefix. Each prefix instruction took the 4 data bits from its byte and shifted them into the central operand register.
Building up a larger value piece by piece.
Exactly. You could string together multiple prefix instructions to build an operand of any size, 8 bits, 12 bits, 32 bits, in that operand register. The next instruction would then use that value.
Clever. Like building numbers digit by digit.
A good analogy. And there was another layer, the oper, or operate instruction. This was special.
How so?
The oper instruction took the value that had been built up in the operand register and treated that value as an extended instruction code, allowing for many more operations beyond the basic 16 function codes.
So some instructions were 1 byte, others might be 2 or more bytes using prefixes and operate.
Yes. It created this variable length but incredibly compact instruction stream. Radically different from the fixed 32-bit instructions of most RISC chips.
And the reason for this complexity was code density, fitting more code into the small on-chip RAM.
Absolutely critical. The early transputers only had 2 KB or 4 KB of on-chip RAM. Making the code super dense was essential to fit meaningful programs in that fast local memory, and it worked. Studies showed something like 70% of executed instructions were single byte.
Okay, another point of difference. RISC generally avoided microcode. Did the transputer?
No, it actually made quite extensive use of microcode, which is that lower layer of control instructions inside the CPU.
Doesn't microcode usually mean slower?
Not necessarily. Despite the microcode, many of those single-byte instructions could still execute in a single clock cycle, keeping performance high. It was a very optimized microcode engine.
And they did something quite advanced with that microcode. formal verification.
Yes, this was really groundbreaking for the time. They used formal methods, rigorous mathematical techniques to prove the correctness of the transputer's microcode. They actually wrote the microcode's logic in Occam, their programming language, and then used tools to formally verify it.
Proving mathematically that the chip's core logic was correct.
Essentially, yes, an incredibly early use of formal methods in microprocessor design. Very sophisticated stuff. And it contributed to the chip's reliability and, they claimed, its performance. David May famously stated the T800 was the fastest floating point microcomputer available when it launched.
A bold claim.
Now, the feature that really defined the transputer, the links, the OS links.
The inter-chip communication highways.
Exactly. Each transputer had typically 4 of these high-speed serial links built right into the hardware. They allowed direct connection to up to 4 neighboring transputers.
How fast were they?
They ran at 5, 10, or 20 megabits per second, which might not sound like much today, but in the 1980s, 20 megabits point-to-point between chips was seriously quick.
And these links were the basis for building larger systems. Compute farms.
That was the idea. You could wire transputers together in grids, rings, cubes, whatever topology suited your problem. Create these farms or networks of processors, all communicating directly via these fast hardware links.
But wasn't there a problem if chips were far apart? The message had to hop between chips.
Yes, that was a limitation of direct point-to-point. Each hop added latency. If a message had to go 10 hops across a large grid, the delay could become significant.
Did Inmos have a solution for that?
They did. A rather neat piece of hardware called the C004 link switch. It was essentially a 32-way electronic crossbar switch for transputer links.
A telephone exchange for transputers.
Pretty much. You could connect up to 32 transputer links to it, and it could connect any input link to any output link with effectively 0 delay. It allowed much larger, more flexible networks and even dynamic reconfiguration, changing the connections on the fly, though the switch itself could sometimes add a bit of overhead.
Okay, let's talk booting and scheduling. You mentioned network booting was possible.
Yeah, very flexible. A pin called boot from ROM controlled it. If asserted, it booted from memory like normal. If not, it just waited for boot code to arrive on any link.
So one master transputer could boot the whole network.
Exactly. The master boots from ROM, then sends customized boot code down the links to all the others. You could tailor the software for each node remotely. Very powerful for distributed systems.
And they had a special debug mechanism, peek and poke.
Haha, yes. A low-level way to inspect or change memory contents and other transputers over the links, even before they were fully booted. Use special message links 0 and 1. Handy for diagnostics.
But maybe the most unique feature was the hardware scheduler.
Oh, absolutely remarkable. Built right into the silicon, not software. It managed multiple processes running on a single transputer and automatically handled the communication over the links.
How did it work?
If a process tried to send or receive data on a link or a channel and the other end wasn't ready, the hardware scheduler would automatically pause or deschedule that process. It wouldn't waste CPU cycles busy waiting.
It would just put it to sleep and run something else.
Instantly. It would switch to another process that was ready to run, all handled by the hardware with virtually 0 overhead. It kept the CPU busy doing useful work. It even had 2 priority levels, high priority for real-time tasks, low priority for general computation.
So OS-like features in hardware.
Deeply integrated, and here's the really clever part. The same hardware mechanism, the same channel communication logic, was used for communication between processes running on the same chip.
Virtual channels in memory.
Exactly. Processes could talk to each other using channels, just like they talk to processes on other transputers via the physical links. The hardware scheduler managed both seamlessly. It blurred the lines between interchip and inter-chip communication and between hardware and OS functionality in a truly elegant way.
Right, let's walk through the transputer family.
Yeah.
It wasn't just one chip, was it? It evolved, started with the T2 series.
That's right, the 16-bit line. The very first prototype was the S43, apparently lacked the hardware scheduler, so it was more experimental. The first real product was the T212.
What did that have?
2 kilobytes of on-chip RAM running at 17.5 or 20 megahertz, a solid 16-bit core. Then came the T222, which bumped the RAM up to 4 KB.
Any other 16-bit models?
The T225 added some useful features like hardware breakpoint support for debugging and a few extra instructions. And there was a specialized version, the M212, which actually had an onboard disk controller, showing their system-on-a-chip ambitions early on.
Then they moved to 32-bit with the T4 series.
Yes, launched in October 1985. The T414 was the first. Quite a powerful chip for its day, around 900,000 transistors, built on a 1.5 micron process.
How much RAM speed?
Started with 2 KB on-chip RAM, 15 or 20 megahertz clock speeds. Crucially, it could address up to 4 gigabytes of external memory, which was huge back then.
So it could handle large data sets if needed.
Definitely. Later, the T425 increased the on-chip RAM to 4 KB and added some instructions from the later T800. And for embedded systems, they brought out the T489.
The cut-down version.
Yeah, lower cost, 20 megahertz, 2 KB RAM, and only 2 communication links instead of 4. Aimed at applications where cost was more sensitive.
But the real star was the TA series, the T800.
Oh, absolutely. Introduced in 1987, the T800 was a major leap. It kept the 32-bit core, but added a full 64-bit floating point unit, an FPU, right onto the chip.
Floating point for scientific and graphics work.
Exactly. And it was a proper FPU, implementing the IEEE 754 standard, which was becoming the benchmark. It also had 4 KB of on-chip RAM and came in 20 or 25 megahertz versions, a real powerhouse for numerical computation.
Did they refine the T800 later?
Yes. The T801 and T805 added things like breakpoint support and, importantly, separate address and data buses on the outside, which could improve performance when accessing external memory.
And Inmos made support chips too. You mentioned the link switch.
Right. The C00432-way link switch was vital for building bigger, more flexible networks. They also made link adapters, the C01 and C02.
What did they do?
They basically allowed you to connect a transputer link to a standard 8-bit parallel data bus. So you could easily interface a transputer network to a host computer, like an IBM PC, through an expansion card, made integration much easier.
Now, software. The transputer was designed with a specific language in mind, wasn't it? Occam.
Yes, Occam was absolutely central to the whole philosophy, developed by David May and others at Inmos, heavily based on Tony Hoare's CSP ideas communicating sequential processes.
Designed specifically for parallel programming.
Explicitly. Occam had features that made concurrency feel natural, not bolted on. The core idea was communication through named channels.
Channels, not shared memory.
Deliberately avoided shared memory. In Occam, processes talk by sending messages over channels. One process outputs to a channel, another inputs from it. It's synchronized. The communication only happens when both sender and receiver are ready.
Why was that better than shared memory?
It avoids a whole class of incredibly tricky bugs common in parallel programming race conditions, deadlocks caused by fighting over shared variables. The channel model is inherently cleaner and safer for concurrent systems.
How did you structure parallel work in Occam?
With simple keywords. You'd wrap sequential code in a SEQ block. Code that could run in parallel went inside a PAR block.
So you explicitly marked parallel sections.
Yes. The compiler could then potentially distribute the different branches of a PR block across multiple transputers if you were building a multi-chip system. It made parallel decomposition very explicit.
Like that sweater knitting example, knitting the parts in parallel, sewing them sequentially.
Well, exactly. PA for the sleeves and body, SEQ for joining them up. And there was another key construct, ALT, for alternation.
What did ALT do?
It allowed a process to wait on input from multiple channels at the same time. Whichever channel became ready first, its corresponding code block would execute. It allowed for reactive systems that could respond to different inputs as they arrived.
And the transputer hardware was designed to run Occam efficiently.
That was the unique part of the development process. They designed the Occam language first, then they built the compiler to generate the most efficient possible machine code from Occam. Then they designed the transputer's CPU instruction set specifically to execute that compiled Occam code as fast as possible.
Wow, language drives the hardware design, not the other way around.
A truly compiler-driven approach. David May used to joke about avoiding bat poop instruction sets, CPUs cluttered with instructions added just for assembly programmers. They wanted hardware optimized for a high-level concurrent language.
And this collaboration got recognition.
Yes. Inmos and the Oxford University Computing Laboratory, where Tony Hoare was, jointly won a Queen's Award for Technological Achievement in 1990 for the Occam development.
Okay, Occam was the ideal, but could you program the transputer in other languages? C, Fortran.
You could, yes. Inmos and third parties released compilers for C, Fortran, Ada, even Pascal and Forth. They understood they needed broader appeal.
Did these other compilers support the parallel features?
Often they did, yes. They usually included library functions or language extensions that allowed you to create processes and communicate via channels, mimicking the Occam model within C or Fortran, so you could still leverage the parallelism.
But the big stumbling block remained the lack of an MMU, preventing standard Unix.
That was a persistent issue, yes. It definitely inhibited porting mainstream Unix variants. People did create Unix-like operating systems for the Transputer, though.
Like what?
There was Minix, a teaching OS. Idris was another early one. Perhaps the most advanced was Helios.
Helios.
Yeah, Helios was designed from the ground up as a distributed operating system specifically for multi-transputer systems. It was quite sophisticated, providing a Unix-like environment across the network, but none of these really broke into the mainstream.
When did the Transputer have its moment in the sun, commercially?
Probably around the time the T800 came out, 1987, 88. Inmos would do these demos at big graphics conferences like SIGGRAPH.
And impress people.
Hugely. They'd show complex rendering or computations running incredibly fast on these unassuming boards full of transputers. People apparently kept looking around for the hidden VX mini computer powering it all, refusing to believe these little chips could do that.
A real eye-opener for parallel potential.
Definitely. And it saw real use in high-performance computing. Edinburgh University built a big system.
You mentioned that it started small, grew to hundreds of T800s.
Yeah, started with 40 chips in 86, scaled up to 400 T800s by 87. Made it one of the UK's most powerful supercomputers at the time. And they used it heavily for research right up until 1994. That's a long lifespan for a supercomputer.
What was the typical way people used transputers? Were they standalone machines?
Mostly no. The most common model was as an accelerator. You'd have a standard host computer, an IBM PC, a Sun workstation, whatever.
Handling the keyboard, screen, disk drives.
Exactly, all the normal I/O and user interface stuff. Then you'd have a board plugged into the host, or a separate box connected, filled with transputers.
And the host would offload the heavy calculations to the transputer network.
Precisely. The transputer system acted like a powerful compute engine, crunching the numbers and sending results back to the host. It's remarkably similar to how modern GPUs work as graphics or compute accelerators. The transputer pioneered that host accelerator model decades ago.
Was the Atari Transputer workstation an example of this?
A classic example, yes. Though commercially, it wasn't a success for Atari. Only about 350 made, apparently, their least successful product ever.
Ouch. But how would it work?
It used an Atari ST mega computer as the host system, handling the operating system, files, user input. Then inside, it had at least one T800 transputer, expandable up to 17, doing the actual processing.
Driving a special graphics card.
Yes, a high-resolution graphics board called the Blossom. The transputers did the calculations and fed the graphics data to the Blossom board, which could drive monitors at impressive resolutions like 1280 by 960. A powerful graphics workstation concept, but too niche or expensive, perhaps.
Okay, so we've seen the vision, the innovation, the early successes, but ultimately, the transputer didn't conquer the world. What went wrong for Inmos?
It's a bit of a sad tale, really. A combination of internal issues, external pressures, and maybe just bad timing. There was reportedly enormous conflict inside the company.
Between who?
Between the U.S. side, which was heavily invested in the memory chip business, a tough, cutthroat market, and the U.K. side, which was championing the transputer. The U.S. folks apparently saw the transputer R&D as a drain on resources needed for the memory distance.
Internal politics undermining the core vision.
Seems that way. And then came a big political shift in the U.K.
Margaret Thatcher's government replacing the Labour one that funded Inmos.
Exactly. The Thatcher government was ideologically opposed to state ownership of industries. They wanted to privatize.
So they sold Inmos.
Yes. And the buyer was Thorn EMI, which was, well, not exactly a tech-focused company.
Thorn EMI, weren't they into music, TV rentals, lighting?
All sorts of things. Described by some as a sprawling basket case. They didn't really have the semiconductor expertise or the long-term strategic commitment needed to nurture something like the transputer. Funding for development reportedly became a struggle.
So unsuitable ownership. Did it get sold again?
Eventually, yes, to SGS Thomson, which is now ST Microelectronics, a major European chip maker. Much better fit technologically.
But maybe too late.
By that point, yeah, probably too late. The momentum had been lost, the market had moved on, ST Microelectronics was capable, but getting the transputer back into the high-performance race would have been incredibly difficult and expensive. That acquisition kind of marked the winding down of the transputer line.
In Inmos try to make a next-generation transputer before the end? a successor to the T800?
They did. They poured a lot of effort into the T9000, codenamed H1. It was meant to be a massive improvement.
What new features was it supposed to have?
A lot of advanced stuff. A much larger 16 KB high-speed cache memory, a deeper 5-stage instruction pipeline for faster execution, a clever circuit called a grouper that could combine several simple instructions and execute them together in one go.
And better communication links.
Definitely. A brand new link protocol called DS-Link, running much faster at 100 megahertz and using packets for more flexibility. This DS-Link tech actually formed the basis for the later IE 1355 standard.
So its link technology lived on.
Yeah.
What else?
A really key addition was the VCP virtual channel processor, hardware dedicated to managing virtual channels over the physical links.
What did that mean for programmers?
It meant your program didn't need to know the exact physical wiring of the transputer network anymore. The VCP handled routing messages transparently through virtual channels, making software much more portable and network design more flexible. A big step forward.
So the T9000 sounded great on paper. Why did it fail to launch?
The fatal flaw was development delays. Long delays. By the time the T9000 was supposed to be ready for release, the competition hadn't stood still.
Other RASC chips had gotten much faster.
Exactly. Those simpler load-store RASC designs had rapidly increased in speed, partly through techniques like superscalar execution. The T9000, despite its cleverness, just couldn't keep up. It failed to hit its performance targets. They wanted a 10x improvement over the T800, but only got maybe 36 mAps at 50 megahertz. Not enough.
So it's obsolete before it even shipped.
Pretty much. There was a rather bleak joke going around at the time. The best host architecture for a T9000 is an overhead projector. Because it seemed perpetually stuck on presentation slides, never quite becoming real hardware. Its cancellation really was the final nail in the coffin for the transputer line.
Okay, let's summarize the main reasons for the decline. Cost was a big one.
Definitely. The T2s were priced too high for the 8-bit embedded market they might have fit into. And the T800, at around $400 a pop, made building those large parallel systems just too expensive for anyone outside specialized research labs or niche industries. The economics didn't scale well for widespread use.
And performance didn't keep pace with RISC.
Initially, the T800 was very competitive, especially in floating point, but RSC chips improved faster. The adoption of superscalar techniques, executing multiple instructions per clock cycle, really left the T800's single pipeline design behind in terms of raw integer performance.
The software ecosystem was another major hurdle. Occam's unfamiliarity. No Unix.
Huge factors. Occam was powerful for parallelism, but had a steep learning curve and wasn't mainstream. The lack of an MMU blocking standard Unix was critical. Developers had existing code bases in C and Fortran. Why rewrite everything for a niche architecture, especially when standard CPUs kept getting faster anyway? Little incentive.
And its fundamental design, stack-based, microcoded, went against the RISC trend.
Yes, architecturally, it ended up looking more like a CISC, complex instruction set computer chip, in a world rapidly moving towards RISC, reduced instruction set computer. The industry voted for large register files and simple load store pipelines, and the transputer had gone a different way.
What about Occam's synchronicity? Was that a downside too?
While elegant, the strict synchronous message passing of Occam and CSP had drawbacks in practice. It made systems potentially quite brittle. If one process stalled waiting for communication, it could deadlock or block others unexpectedly. Real-world systems often need more resilience, more tolerance for timing variations or faults. Occam's purity could make systems too static and very fault-intolerant.
And that internal battle, pragmatists versus purists.
That seems to have been crucial, too. The purists wanted to stick to the Occam-centric vision, believing it was the only way to truly achieve optimal parallelism. The pragmatists argued for better C support, Unix ports, meeting the market where it was. The purists largely won the internal arguments, keeping the focus sharp.
But they lost the wider market war.
Arguably, yes. A more pragmatic approach might have secured a larger foothold, even if it diluted the original vision somewhat.
But the story doesn't end there. Despite the commercial failure, the transputer left a real legacy, right? It was used in some cool places.
Oh, absolutely. Its influence is significant and surprisingly widespread even today. In its heyday, it was big in massively parallel computing, HPC. Companies like Mako Scientific, founded by ex-Inmos people, built powerful supercomputers using transputers, floating point systems, Parsatech, Parses too.
Her research labs loved them.
Definitely. Places like Bristol University, the Edinburgh Supercomputer Project we mentioned. It was also used in big science, like the ZE West particle physics experiment at DASY. In Germany, they had over 300 transputers processing detector data.
What about more mainstream commercial uses?
It found niches there too. Image processing, R.R. Donnelley used them. High-speed data acquisition systems from companies like Jägermesstechnik. AVM, the German router company, used them in early ISDN controllers. Medical imaging, radar systems, even early virtual reality hardware like Division Limited's Provision 100 system.
And it even went to space.
It did. The radiation-tolerant T-805 version flew on the French Myriad satellite platform used on missions right up until 2015. And NASA's HATE-2 satellite used 4 T-805s. Its low power and deterministic nature were valuable there. It's also spurred development in asynchronous algorithms.
So its influence goes beyond just the hardware. What about direct descendants or related tech?
Well, the ST20 microcontroller core from STMicroelectronics was a direct descendant using T9000 technology and found its way into millions of set-top boxes and GPS devices. Very successful in the embedded space.
And David May, the architect, started another company, XMOS.
Yes, XMOS. And their X-core chips carry strong echoes of the transputer. They feature multiple processor cores on one chip, hardware support for parallelism, and they're programmed in XC, a variant of C with CSP-style communication primitives built in.
Used for software-defined interfaces.
Exactly. You can program the chip's pins to behave like almost any standard interface. USB, Ethernet, audio protocols, all in software running on these parallel cores. Very flexible, used a lot in pro audio gear.
And that T9000 link technology, DS-Link, became SpaceWire, used on the James Webb Telescope.
That's right. The core ideas behind DS-Link evolved into the IE 1355 standard, which then became the basis for SpaceWire, a standard communication network for spacecraft. So transputer DNA is literally flying on the most advanced space telescope ever built. Amazing lineage.
Even huge supercomputers, like IBM Blue Gene, are seen as inheriting the spirit.
Many people see Blue Gene as a real-world incarnation of the transputer dream. Why? Because it was built from vast numbers of relatively simple, identical processing nodes, systems on chip, all interconnected, working in parallel, very much in the transputer spirit.
And the whole idea of network on chip.
Network on chip, or NoC, which is fundamental to almost all modern multi-core processors. Think Intel, AMD, ARM chips in your phone or laptop, specialized chips like Cell or Telera. That whole approach of having processors communicate over an integrated network fabric right there on the silicon. That resonates directly with the transputer's core concept of integrated links. The industry eventually arrived where Inmos started.
And Inmos itself helped build the tech scene in Bristol.
Absolutely. Inmos and the Transputer Project attracted and trained a huge amount of talent, helping establish Bristol as a major UK hub for microelectronics design, a reputation it still holds today. Many successful chip design companies spun out of Inmos or were founded by ex-employees.
And finally, the software ideas. CSP, Occam. Did they survive?
Conceptually, yes, very much so. Tony Hoare's communicating sequential processes model, which Occam implemented so faithfully, is alive and well. Look at the Go programming language from Google. Its channels for concurrency are pure CSP.
Yo, channels come from CSP. Didn't know that.
Directly inspired. Erlang's actor model is philosophically similar, focusing on message pressing between independent processes. Even newer languages like Pony use related concepts. The idea of building concurrent systems through explicit, safe communication rather than messy shared memory has proven incredibly powerful and enduring.
So it really feels like the fundamental transputer motive remains extremely relevant today.
It absolutely does. The industry eventually hit the same power and heat walls that Inmos foresaw. And the solution? Multi-core, many-core processors. Putting lots of simpler cores on a chip instead of one giant power-hungry one.
And needing efficient ways for those cores to communicate.
Exactly. The solutions they found, networks on chip, sophisticated cache coherency protocols, are arguably a little different in essence from those proposed by Inmos decades earlier. The transputer was just way ahead of the curve.
Well ahead of its time seems like the perfect summary. It influenced so much, even if it didn't achieve the commercial success itself.
It paved the way. Its journey, even in failure, provided crucial lessons and inspiration for the technologies that define computing now.
So, wrapping this up, the transputer. What an audacious vision looking back. A pioneering attempt to tackle those core computing limits head-on by embracing parallelism from the silicon up.
Building these self-contained computers on a chip, designed explicitly to link up and cooperate. Truly innovative for the 80s.
But we saw its commercial fate. Despite the innovation, despite finding those niche markets, the internal conflicts, the wrong ownership, the sheer pace of competition, it just couldn't sustain itself.
A familiar story in tech, perhaps? Brilliant ideas aren't always enough on their own. Timing, funding, market fit, internal cohesion, they all matter hugely.
Yet its legacy is undeniable. Even if the transputer chip itself faded, those core ideas, hardware links for parallel communication, integrating OS functions into the silicon concurrency-first programming models, they were incredibly influential.
They planted seeds that grew into many of the technologies we take for granted today. Network on chip, multi-core architectures, even programming language features.
It really makes you think. The transputer story is this powerful reminder, isn't it?
Yep.
Sometimes the most groundbreaking ideas are just early, ahead of their time.
Its journey, even the parts that look like failure, helped clear the path for the multi-core world we live in now. The supercomputers, the sags in our pockets.
So here's a final thought to leave you with. If the transputer was ahead of its time then, what other technologies or ideas might be out there right now, maybe struggling, maybe niche, that are quietly laying the groundwork for the next big shift? What ahead of its time innovations are shaping our future as we speak?